Bismillah ar-Rahman ar-Rahim. We have an infinite product, n from 2 to infinity, e 1 minus 1 over n squared, all to the power n squared. Let's study the logarithm of this product. The logarithm of the product is the sum of logarithms. This is log e, which is equal to 1, plus log 1 minus n squared, all to the power n squared. So we can take this n squared outside, and we have log 1 minus 1 over n squared. This is log n squared minus 1 divided by n squared, which is log n squared minus 1 minus log n squared. These two terms are multiplied by n squared. What I will do now is to write the summand as an integral. Note that if we integrate from 0 to 1, 1 over n squared minus y, we get log n squared minus y, and then we have 0 and 1 as our limits of integration. If y is 0, we get log n squared. If y is 1, we get log n squared minus 1. These two terms can be written as integral y from 0 to 1 minus n squared, to account for those guys, divided by n squared minus y. And if we put a 1 here, the integral of 1 from 0 to 1 is 1. The summand can be written as integral y from 0 to 1, 1 minus n squared over n squared minus y. This is n squared minus y minus n squared over n squared minus y. So this is y divided by y minus n squared. Let's do the substitution. Y equal to x squared. dy is 2x dx. This becomes x squared. So in the numerator, we have 2x cubed. Downstairs, we get x squared minus n squared. Assuming we can interchange the order of integration and infinite summation, this is integral from 0 to 1, sum n from 2 to infinity. We can take x squared outside the summation, and in the sum here, we have 2x divided by x squared minus n squared. We do this to make our summation look like the expansion of the cotangent function. Pi cotangent by z is 1 over z plus 2z summation n from 1 to infinity, 1 over z squared minus n squared. Consequently, this summation here can be written as pi cotangent by x minus 1 over x. Note that this summation starts from 1, our summation starts from 2. We need to remove the term corresponding to n equal to 1. This is 1 over x squared minus 1, and then we have 2x in the numerator. Multiplying by x squared, the logarithm of the infinite product is the integral from 0 to 1, pi x squared cotangent pi x minus 2x cubed divided by x squared minus 1. Let's subtract and add 2x. Minus x minus 2x is minus 3x. Then we have 2x minus 2x cubed over x squared minus 1. If we have a common denominator, x squared minus 1, upstairs we have 2x cubed minus 2x. Then we have minus 2x cubed. These two terms go away, and we get 2x divided by 1 minus x squared. The integral of minus 3x is minus 3 over 2x squared, and when we use the limits of integration, we get minus 3 over 2. The logarithm of the infinite product is minus 3 over 2 plus integral x from 0 to 1, 2x over 1 minus x squared plus pi x squared cotangent by x. Let's focus on this integral. Suppose that we have alpha in the open interval between 0 and 1. We have this integrand, and we are integrating from 0 to alpha. We later take the limit as alpha approaches 1 from below. The antiderivative of this part is the natural logarithm of 1 minus x squared. When we use the limits of integration, we get log 1 minus alpha squared minus log 1, which is 0. So we have minus log 1 minus alpha squared. The antiderivative of pi cotangent by x is the logarithm of sine pi x. We do integration by parts. When we use alpha, we get alpha squared log sine pi alpha. And then we need to take the limit of x squared log sine pi x when x approaches 0 from above. Also, when we do integration by parts, we will get minus integral from 0 to alpha log sine pi x, then the derivative of x squared, that's 2x. Let's investigate this limit. Limit as x approaches 0 from above of log sine pi x times x squared, here written as 1 over x squared. If x is 0, sine 0 is 0, and as the argument of the logarithm approaches 0 from above, the logarithm approaches minus infinity. Downstairs, as x approaches 0, 1 over x squared tends to infinity. We have infinity over infinity situation. We can apply L'Hopital's rule. The limit is equal to the limit of the ratio of the first derivatives. Downstairs, we have minus 2 over x cubed. Upstairs, we get 1 over sine pi x. Then by applying the chain rule, we have also pi cosine by x. We can take this minus 1/2 outside. Note that there is no problem if we put this x equal to 0. Cosine 0 is 1. Our limit becomes the limit as x tends to 0 of pi x over sine by x, but we actually have here x cubed, so there is also the limit as x tends to 0 of x squared. Of course, this limit is 0, and this limit is finite. This limit is exactly equal to 1, so the overall limit is equal to 0. This term here is equal to 0. Now let's take the limit as alpha approaches 1 from below. The integral becomes from 0 to 1. What about these two terms? The limit as alpha approaches 1 from below of alpha squared log sine by alpha minus log 1 minus alpha squared. Let's write this as minus log 1 minus alpha minus log 1 plus alpha. If we put alpha here equal to 1, we get minus log 2. Then we have the limit as alpha approaches 1 of alpha squared log sine by alpha minus log 1 minus alpha. Let's subtract 1 from alpha squared and add 1. We get alpha squared minus 1 plus 1 log sine by alpha minus log 1 minus alpha. We can split the limit into two limits. In the first one, we have alpha squared minus 1 times log sine by alpha. Then we have log sine by alpha minus log 1 minus alpha. This is log sine by alpha over 1 minus alpha. We can write down this limit as the limit as alpha tends to 1 of log sine by alpha, which tends to minus infinity as alpha tends to 1. Downstairs, we have the reciprocal of alpha squared minus 1. And this tends to minus infinity as alpha tends to 1 from below. Applying L'Hopital's rule, the derivative of the numerator is 1 over sine by alpha pi cosine by alpha. The derivative of the denominator is minus alpha squared minus 1 to the minus 2. We can write this in the numerator as alpha squared minus 1 squared. And then we have 2 alpha. If alpha tends to 1, this part tends to 2. Cosine by alpha tends to minus 1. We still have to handle these two terms. We are in a 0 over 0 situation. Applying L'Hopital's rule again. Upstairs, we get 2 times alpha squared minus 1 times 2 alpha. Downstairs, we get pi cosine by alpha when we differentiate sine by alpha. Now, if alpha tends to 1, we get minus pi downstairs, which is not problematic. And then in the numerator, we get 0. So the overall limit is equal to 0. What about this term? Note that the logarithm is a continuous function, so we can take the limit inside. We have log limit as alpha tends to 1 from below of sine by alpha over 1 minus alpha. This is 0 over 0. If we set alpha equal to 0, applying L'Hopital's rule, this is equal to log the limit as alpha tends to 1 from below of pi cosine by alpha divided by minus 1. Cosine pi is equal to minus 1. Thus, the limit is log pi. Don't forget this minus log 2 here. We have the two terms, minus log 2 plus log pi, but we still have this integral here, x from 0 to 1 of x log sine by x. Let's call this integral big omega. If we replace x by 1 minus x, sine pi minus pi x is sine by x. This x is changed to 1 minus x. We can write omega as the average of these two integrals. That is, we sum them and then divide by 2. The advantage of this step is that when we sum the two integrals, x plus 1 minus x is equal to 1. Omega is 1/2 times the integral x from 0 to 1 of log sine by x. Note that sine by x is symmetric about x equal to 1/2. So this integral is double the integral from 0 to 1/2. 2 times 1/2 is 1. Omega is equal to the integral x from 0 to 1/2 log sine by x. If we replace x by 1/2 minus x, sine by over 2 minus by x is equal to cosine by x. So omega is also equal to this integral here with cosine rather than sine. To get omega, note the following. If we integrate x from 0 to 1/2 log 2 sine by x cosine by x, this is log 2 plus log sine by x plus log cosine by x. If we split into 3 integrals, we get log 2 times 1/2, and then the integral with sine, that's omega, and the integral with cosine is also omega. So this integral here is 2 omega plus 1/2 times the natural logarithm of 2. But we can evaluate this integral in a different way. 2 sine by x cosine by x is sine 2 by x. This function here is symmetric about 1/4. So this integral is double the integral from 0 to 1 over 4. Here I'm writing the integral using the dummy variable of integration y. Let's do the change of variables. X is equal to 2y. Then 2 dy is dx. Log sine 2 pi y is log sine pi x. When y is 0, x is 0. When y is 1/4, x is 1/2. And this integral is exactly omega. So omega is equal to 2 omega plus 1/2 log 2. This means that omega is minus 1/2 log 2. To get this integral here, we multiply by minus 2. So we get log 2, and we had those two terms. We are left with log pi. The logarithm of the infinite product is minus 3 over 2 plus log pi. If we exponentiate, we get e to the minus 3 over 2 plus log pi. This is equal to pi e to the minus 3 over 2, or pi divided by e, the square root of e. This is the value of this infinite product.